Good morning. Today I will talk about the need for quantum mechanics and the inadequacy of classical mechanics which results in the need for quantum mechanics. In the beginning of the first quarter of last century, the scientists understood that we need a paradigm shift in the way we looked at nature and understood physics. One of the main reasons for this was the realization of the existence of an atom. They were in for a step-by-step demolition of their long-cherished ideas and theories of classical mechanics. Now, in this talk, I will follow the method of lecture which is given in the book The Modern Quantum Mechanics by J.J. Sakurai. Now, this method is different from the usual introduction to quantum mechanics, which is more or less an historical perspective of quantum mechanics. So, here I would give first a shock and surprise treatment which would make us understand that our concepts of classical mechanics are inadequate, which will confuse us, which will awaken us and make us reconsider the thoughts, reconsider the theories of classical mechanics. So, let us first look at the Stern-GERLACH experiment. Now, the Stern-GERLACH experiment consists of an oven where silver atoms are heated. The silver atoms escape through the orifice. They are collimated by the two pinholes which acts like a collimator to only select the atoms that are in the x direction. The x direction would be the horizontal direction. Now, these silver atoms after the collimation move into a region of inhomogeneous magnetic field created by two magnets. The magnets are constructed in such a way that one of the magnets have a sharp edge, giving rise to an inhomogeneous magnetic field. The need for an inhomogeneous magnetic field would be explained later on. Now, these atoms, after traveling through the inhomogeneous magnetic field, they are received on a screen. If we look at the atoms from in their direction, then the magnets would look as shown in the extreme right. So, you have at the top a magnet which has the north pole which is having a sharp edge, and the bottom you have the south pole, that is the magnet which is flat. The field will be from the north to south, that would be our z axis. Okay. So, let us first look at the simplified model of the silver atom. The silver atom consists of 47 electrons, 46 of which there is a nucleus, 46 of which is within the closed shell, and you have a lone 47th electron which is in the 5s orbital. This is in the 5s orbital. The 5s orbital ensures that there is no orbital angular momentum, and only the spin would be the contribution to the angular momentum for the silver atoms. So, the silver atom, the contribution to the angular momentum would only be due to the spin. Now, when these silver atoms see the inhomogeneous magnetic field, they experience a force. Now, let us look at the equations and try to understand. The interaction energy that these silver atoms would experience is given by minus mu dot B, where mu is the magnetic moment of the silver atom, which is due to the lone silver atom in the 5s orbital, and the magnetic field is the field that is produced by the magnets. Now, this magnetic moment of the silver atom is directly proportional to the spin. As I have mentioned before, the silver atom, the lone electron is in the 5s orbital. So, the angular momentum is 0 and only the contribution to the angular momentum would be from the spin. So, the magnetic moment is directly proportional to the spin, and the magnetic moment would be given by the charge of the electron divided by the mass of the electron times the velocity of light into the spin. Now, the interaction energy would be U equal to minus mu dot B, which is equal to E minus E by MEC into S dot P. Now, let us consider two cases. The first case where the spin is parallel to the magnetic field. The case 1 where the spin is parallel to the magnetic field. In this situation, S dot B would be S B cos 0, and that would be just S B. So, we have the interaction energy equal to minus E by MEC into SZ BZ, because in the Z direction the field is only along the Z direction, and we will take it to be BZ, and the spin is parallel to, we are considering the spin that is parallel to the magnetic field. So, we will consider it to be SZ, the Z component of the spin. Now, the force that these silver atoms would experience would be given by minus dou U by dou Z. Now, if we substitute the value of U, then we have the force is equal to E by MEC SZ dou BZ by dou Z. Now, the force is directly proportional to the gradient of the magnetic field. This explains that we need a inhomogeneous magnetic field for the electrons to experience the force. If the magnetic field was homogeneous, then the force would be 0 and they would go undeflected. Okay. Now, if we look at the equation of force and we introduce the negative charge of the electron, then the force would be minus E MEC SZ dou BZ by dou Z. The force is in the opposite direction to that of the field. So, the force would be upward. So, in this case, when the spin is parallel to the magnetic field, the force would be upward. So, we have an upward force. Now, let us consider the second case. In the second case, where the spin is anti-parallel to the magnetic field. Now, in this case, our interaction energy would still be minus mu dot B. Now, we have our interaction energy equal to minus E by MEC S dot B, where the S dot B would now be equal to S B cos 180, which would be giving us a plus sign here. So, we have an interaction energy which is given by E by MEC SZ BZ. Now, the force would be minus dou U by dou Z. So, the force would come out to be minus of this quantity here, and then ultimately when we take the negative charge of the electron into consideration, you have a positive force. That means that the direction of force would be along the direction of the B, that would be the force would be downward. So, now here we have looked at the two cases. The case 1 where the spin is parallel to the magnetic field, in this case we have an upward force, and the case 2 where the spin is antiparallel to the magnetic field, and in this case we have an downward force. Now, if we consider the electrons and the silver atoms classically, and the origin of spin to be due to the spinning of the electron, which would be how classical mechanics will look at it, then the situation, the result of the experiment that we would expect would be a straight line on the screen. So, what we would expect then would be a straight line on the screen. Now, let me rub it and describe the result. Now, as we have seen, there are the two cases. There is one case where the spin was parallel to the inhomogeneous magnetic field, and the other case where the spin was antiparallel to the applied inhomogeneous magnetic field. Now, in both the cases, the force was acting on the silver atoms, and when they were parallel, the force was in one direction, and when they were antiparallel, the force was in the opposite direction. Now, if we consider the electrons and the atoms to be classical, then there is nothing much sacred about this parallel and antiparallel directions. The electrons, if we consider to be as rotating tops, and this rotation giving rise to the spin, then the random orientation of the silver atoms inside the oven would ensure that the electron angular momentum or the spin would also be randomly oriented. So, instead of just having the parallel and anti-parallel directions, we will also have directions in between, and between the parallel and anti-parallel direction. Now, if we consider the case where the spin is perpendicular to the applied magnetic field, in such a case the force acting on the silver atoms would be 0, because in that case the angle between them is 90 degree and cos 90 is 0. So, if the spin was in between 0 and 90 degree, then you will have a force which is less than when the angle was 0, that is when they were parallel, the spin and the magnetic field was parallel. So, you will see classically a uniform distribution of silver atoms on the screen, but when they looked at the screen, they saw two spots. And these two spots showed that the spin cannot take any random value as predicted by classical mechanics. Spin can take only two values. So, this resulted in the understanding that the spin is quantized. So, Stern-Gerlach experiment in principle gave us the quantization of spin and broke the notion of classical mechanics, and explained that the spin cannot be and told us that the spin cannot be explained by the usual classical mechanics as a top spinning, but it has to be taken as the intrinsic angular momentum for the electron. Now, here we have seen that classical mechanics was inadequate to explain the results of Stern-Gerlach experiment, and so a new theory was needed, and this new theory was called quantum mechanics, and more about the Stern-Gerlach experiments I would give more about Stern-GERLACH experiments. I will talk in the next lecture, where I would show you a sequence of Stern-GERLACH experiments and the results of which would go against the classical understanding of objects.